Astronomy relies on scale. We point robotic telescopes at the Milky Way's center, monitoring millions of stars, waiting for one pixel to change brightness. Usually, these changes are slow and predictable. A background star gets brighter, then dimmer over the course of a month, as an invisible object drifts in front of it. But on the night of August 10, 2005, the OGLE and Planet networks caught a disruption. Right in the middle of a standard 11-day brightening event, the light spiked. It lasted only a few hours. This animated curve plots brightness over time. Notice the smooth bell curve, interrupted by a sharp spike near the peak. From this brief deviation, astrophysicists extracted a specific mass ratio, an orbital distance of 1.61 Einstein radii, and a planetary mass of 5.5 Earths. The question is how researchers looked at a transient, hours-long blip in light intensity and used it to definitively map a 5.5 Earth-mass planet located 20,000 light-years away. The difficulty of this discovery is that neither the planet nor its host star emitted any detectable light captured by our telescopes. We didn't see the planet, and we didn't measure the gravitational tug on its star. The detection relied strictly on the passive gravitational deflection of a distant background star's light. This deflection operates on the foundational principles of general relativity, which establish that massive bodies bend the actual fabric of spacetime around them. Because this lensing effect is entirely geometric, we can't directly image the system. Instead, we must treat it as an inverse problem. We take the empirical observation, the light curve, and work backward through complex calculus to deduce the masses that caused it. To decode OGLE-2005-BLG-390, we need to reconstruct the mathematical machinery of binary microlensing. We have to look at exactly how an invisible vase creates such a highly specific optical signature. We start with the simplest theoretical scenario, a single, solitary point mass drifting between a background source star and our telescopes. This animated diagram illustrates a perfect 3D alignment between an observer, a lens mass, and a source star. The gravitational field of the lens bends the source star's light rays equally in all directions, forming a perfectly circular halo known as an Einstein ring, denoted by theta E. In reality, perfect alignment is incredibly rare. The background star typically passes at a slight offset. We measure this closest approach distance as the impact parameter, U. The total magnification of the source star is strictly a function of this distance U, defined by this equation. As the source moves closer to the lens, U decreases, and the total magnification creates a smooth, predictable peak. This simple rectilinear motion of a single star passing a single lens perfectly describes the main 11-day envelope of the OGLE 2005 event. As long as a lens is a solitary star, the resulting magnification curve will always be perfectly symmetrical. Any localized, sharp spike breaks that symmetry, providing irrefutable mathematical proof of a secondary mass. That sharp spike in August tells us the OGLE 2005 host star is not alone. To account for its companion, we have to update the math. We map the binary lens equation in the complex plane. This model splits the single central mass into two unequal masses, the star and the planet, and introduces a new variable, epsilon I, which represents the planet's mass fraction. Adding this secondary planetary mass shatters the perfect radial symmetry of the Einstein ring. The gravitational field is pulled out of shape. Because the lensed images are now stretched and distorted, we calculate their new total area using the determinant and the Jacobian matrix. Look at this equation mapping magnification. There are specific physical locations in this warped field where the Jacobian determinant approaches exactly zero. Dividing by zero pushes the theoretical magnification toward infinity. Carefully, we call these illuminated boundaries of infinite magnification caustics. The transient anomaly on August 10th wasn't caused by the planet directly emitting or blocking light. It happened because the background star physically intersected one of these invisible, mathematically defined caustic boundaries. These caustic boundaries do not form randomly. Their exact geometry is strictly dictated by two variables: the mass ratio between the star and the planet, Q, and their projected separation distance, D. Depending on that distance, every binary system falls into one of three distinct topological regimes: close, resonant, and wide. In the close regime, where the orbital distance d is much less than 1, the planet orbits tightly against the star. This creates a small central caustic and two distinct planetary caustics further out. As the planet shifts outward to the resonant regime, sitting right on the Einstein ring where d equals 1, the three caustics stretch and merge into a single, massive six-cusped geometric hazard. Finally, in the wide regime, where d is much greater than 1, the planet orbits far away. The gravitational strain tears that massive caustic apart into a central shape and a separate distant planetary caustic with four cusps. We can take this strict geometric rulebook and cross-reference it against the OGLE-2005 data table, which recorded a projected orbital distance of 1.61. Because 1.61 is greater than 1, the OGLE system is definitively a wide topology. This physical measurement places the 5.5 Earth mass planet far out in the cold, distant reaches of its solar system. There is a limitation to this mapping process. The equations naturally output relative ratios, like the mass fraction Q, but they don't immediately give us physical masses in Earths or suns. We also run into a mathematical mirror effect known as offset degeneracy. When Q is small, two entirely different physical architectures, an inner orbit of d and an outer orbit of 1 over d, can produce identical magnification light curves. To break this degeneracy and find the true scale, we measure the finite source effect. Instead of treating the background star as an infinitely small point, we calculate the exact time it takes its actual physical disk to cross the caustic boundary. The second essential mechanism is microlens parallax. A microlensing event takes months to unfold, and during that time, the observer is not sitting still. Earth moves along its curved orbit around the sun. This non-rectilinear motion slightly distorts the baseline light curve. We are observing the lens from a continuously shifting viewpoint, which provides the precise geometric perspective needed to break the dual solution symmetry. We take the raw mass ratio of 7.6 times 10 to the negative fifth, and we apply these parallax and finite source corrections. The mathematical probabilities collapse into a single physical truth. Breaking that mathematical ambiguity allowed the research team to definitively classify the components. They found a dim 0.22 solar mass red dwarf, hosting a cold 5.5 Earth mass planet. Transit and radial velocity methods have found thousands of exoplanets over the last few decades, but those techniques suffer from extreme observational biases. Both-of-nose detection methods almost exclusively require incredibly massive planets orbiting dangerously close to their host stars in order to generate a measurable signal. Large, close-in gas giants dominate our early exoplanet catalogs simply because their extreme mass and tight orbits make them the easiest to detect. Gravitational microlensing is different. It is entirely blind to the star's brightness, and it doesn't care about the gravitational tug. Because the technique relies entirely on geometric deflection, microlensing can peer directly into the snowline, the freezing, distant orbital zones between 1 and 10 astronomical units, where planets are simply too cold and dim to be seen directly. Mapping the complex boundaries of these mathematical caustics provides astrophysics with its only viable tool for finding cold, low-mass planets hiding in the outer dark of their solar systems. OGLE-2005-BLG-390Lb secured its place in history precisely because it was the very first cold super-Earth ever discovered. Since 2005, high-cadence surveys like KMTNet applied these exact Jacobian mathematical models to map hundreds of similar microlensing events across the galaxy. This chart maps exoplanet mass against orbital distance. Notice the dense cluster in the bottom right, low-mass planets on wide orbits. Compared to sparse data from other methods here, microlensing proves cold super-Earths are actually the Milky Way's most common planets. By tracking a single, localized spike in brightness and running it backward through the topology of the complex plane, astrophysicists were able to map the invisible. They proved that freezing, unseen worlds, exactly like OGLE-2005-BLG-390Lb, form the standard planetary architecture of our galaxy.